Hello everybody. Here I have a UPS power backup which converts 12 volts DC internal battery to 115 volts AC output. This multimeter here shows around 118 AC voltage when the converter is plugged into the grid. When I disconnect the unit from the electrical outlet, the internal battery voltage is converted into AC. But hold on a second. It should be 115 AC volts. But we have here only 87 volts AC. Who is cheating on us? The converter? The meter? Let's find out. Here I have a 35 Canadian dollars multimeter. This one here is $200. For this one you can spend $400. And here is a 10 years old Canadian Tire brand, back then $50 multimeter. All of them show give or take 119 volts AC. When I pull the plug, the cheapest and the most expensive show around 115 AC voltage, while the other two display around 86-87 volts AC. What is going on here? To answer this question, we must notice first that two of those meters are true RMS meters. The other two don't have this marking. And in this true RMS designation, we have the answer to our question. An oscilloscope will help us to demystify this puzzle. This device will show us how the voltage changes with time, and we will see the shape of AC voltage from the grid, and we will compare it to the AC voltage generated by the converter inside our UPS power backup. Regular AC voltage in electrical outlets has a sinusoidal shape, here passed through a transformer. Well, one can plug it into the outlet directly, but there is a risk of burning down the scope. Better safe than sorry. On the other hand, the AC voltage generated by the converter looks more like a Minecraft sine wave. As in pure sinusoidal signal, the voltage here goes from 0 to a certain peak value, then goes back to 0, and then changes polarization, just like the sine wave signal. Time to pose the question. What do we really measure with a voltmeter? The peak value? The average value? The mean of the absolute value? Actually, people are interested more in the true root mean square value of the signal, be it voltage or current. In general, we ask how much energy we can draw from a current without looking into the shape of it. We compare the AC alternating current to the DC direct current that will give us the same heating effect in a comparable period. So in true RMS, we don't care about the peak value or the shape of the current. We look at the final product, the heat that is generated by the AC current on the specific resistive element, and compare it to the same value thermal effect created on the same resistive element by the DC current in the same period of time. Complicated? You can always calculate it from this equation, where lowercase I is the current as a function of time, or for the RMS voltage, such an equation. For sinusoidal AC current, its RMS value is in such a relation to the current peak value. Similarly, voltage RMS relates to the peak value in such a way. It means that in order to get RMS value, we must multiply the peak value by 0.707. Multimeters that are not true RMS meters measure a mean of the absolute value. In other words, an average rectified value. Assume that they measure sinusoidal current or voltage when set on AC function selector, and using their internal algorithm, multiply this value by 1.11. Obviously, we talk about digital meters here. True RMS meters are equipped with a more sophisticated algorithm that factors in the shape of the measured output and provide true heat equivalent to the DC signal value. That is why not true RMS meters are good only to measure DC or sinusoidal AC signal. When the AC signal is not pure sinusoidal shape, non-true RMS meters provide inaccurate readings. For our first converter, the true RMS value was around 115 volts. The non-true RMS meter was displaying around 87.5 volts AC. Here I have true RMS voltage from another converter. It is around 115 volts. We can tell from the scope that the peak value of this signal is greater compared to the previous one. And this time the non-true RMS meter shows around 91 volts AC. What about situations when the meter shows presence of a voltage when there is virtually none, or doesn't show voltage when it is present? Here I have a mock-up of electrical outlets. I turn the selector into AC voltage on the meter, and it is normal that it shows presence of a very small voltage when the test leads are not connected anywhere. Then I plug the test leads into the first outlet, and I plug my mock-up into an electrical outlet. We have around 120 AC voltage here. Then I switch the leads into the second outlet, and here I have about 108 volts AC. An electric bulb lights up in the first outlet. But when I plug it into the 108 volts outlet, there is no light. At this voltage, it should at least glow a bit, but nothing. I switch the selector to low Z function, low internal impedance. When I plug it into the first outlet, it shows once again 120 volts AC. Leads into the second outlet, and this time we have only 0.3 volts AC. An outlet tester indicates in the first outlet that everything is fine and dandy. Green light. The tester shows nothing in the second outlet. The power is disconnected, and here we have wires connected to the first outlet. Hot wire into the first outlet, and then it is connected to one prong of long extension cord. The second prong goes into the hot terminal of the second outlet. And there is no electrical connection between the two conductors. The white wire connects neutral terminals of the two outlets. This is an example of a ghost voltage. It disappears when you plug in any device or probe it with a voltmeter with low Z function. When you have a ghost voltage in your wires, don't call Ghostbusters. Call an electrician. I elaborate more on the subject in my other video. Another situation. The bulb doesn't illuminate when plugged in. Does it mean that we don't have a voltage there? Use another digital multimeter function that indicates voltage without contact. Even though the bulb doesn't illuminate, we have voltage here. When we measure the voltage, it is only 5.5 volts. And this is the high voltage that we are warned about by the meter. No voltage at all when we switch to low Z function. Is it a ghost voltage again? The outlet tester indicates open neutral. This is the situation. Neutral is disconnected. The hot wire is energized. There was a real danger. The current can flow only in a closed circuit. If we touch the hot wire, the circuit will close through our body, and current will flow, causing an electric shock, or even death. Another example. About 120 AC volts in the outlet. But the bulb doesn't illuminate. At the same time, voltage drops to about 90-95 volts. In the low Z function, we read 7.5 volts. The outlet tester shows again an open neutral. This time, using a resistor, I simulate either a loose or oxidized connection. Using a multimeter, we should know how to interpret the readings. And probing a circuit, we should have an idea what we can expect. Measuring an AC circuit, the function selector should be at AC. Otherwise, we will not detect the voltage. Same with a DC. Don't measure it in AC function. Don't plug in test leads just to see what will happen. You should understand what you are about to be testing. Like in this case, you will short the circuit and possibly destroy something. In AC current function, the multimeter really measures the voltage drop on a shunt resistor and by the Ohm's law displays current value related to the voltage drop. Before using our device, we should know its limitations. For example, this digital multimeter handles up to 600 volts, but only within 45 to 1000 Hz frequency of an AC voltage. And its accuracy drops at a higher frequency. AC current measurement is even more limited to only 45 to 500 Hz. When we are talking about metrology, I recommend this channel. There you have an academic, Professor Peter Burnos, at AGH University of Science and Technology in Kraków, Poland. He tests and compares different brands of multimeters, explains how to measure different signal parameters, explains how to choose an oscilloscope, which power supply is best for our application. Just turn on English subtitles. Till next time.